Great. All right, it's recording now. So good morning. So let's start with the starter questions. So today's topic is going to be light waves. So this is another webinar on waves, but this is the final webinar of our sort of waves section of the year. So my starter questions are, again, thinking back to last week's webinar. So the first one is a true or false question. So all electromagnetic radiation travels through space at the same speed. Is this true or false? And then question 2 is also about electromagnetic waves. So light waves and microwaves travel at the same speed, but light waves have a shorter wavelength. So which of these two waves would have the higher frequency? And I've got the wave equation triangle at the bottom for you guys to look at there. And then for a thinking question, this isn't super related to this week's topic, but I thought it was a fun question to ask. So which of these two squares do you think is darker, A or B, in this picture that I've got there? So if I could have those polls up, Ms. McKinley, for the starter questions. Great, and I can see that you guys are still joining. So welcome to everybody who's just joined. I've got these starter questions up for you guys to look at now. And I'll wait a while for you guys to answer them. All right, a bunch of you guys are voting. That's great, but I'm gonna give it another few more seconds for you guys to get your answers in. All right, a few more people are still voting, so I'll give it 10 more seconds. Great. All right, so let's start by going over these questions. So for question 1, all electromagnetic radiation travels through space at the same speed. So this is actually true. So all of the forms of electromagnetic radiation, so that's infrared, microwaves, radio waves, visible light, gamma rays, X-rays, all of them travel through a vacuum at the same speed. So they all travel at the same speed of light through a vacuum. And then question 2, so light waves and microwaves travel at the same speed, but light waves have a shorter wavelength. Which of these two waves have a higher frequency? So you guys did great on this question. So light waves actually have a higher frequency. And we can see that by looking at this wave triangle at the bottom. So if their wave speed is the same, and wave speed equals frequency times wavelength, if the frequency of light waves, or if the wavelength of light waves is shorter, that means that the frequency has to be higher, whereas microwaves have a longer wavelength, so their frequency is going to be lower. So great job on those questions. And then for our thinking question, this is actually an optical illusion. So we're talking about light waves today, so I thought it might be fitting to do an optical illusion for our starter question. So the question was, which of these two squares is darker, A or B? And they're actually the same color, which is a little funny because it looks like A is a lot darker than B, but that's actually just because of the context of the squares. So the sort of amount of light, the sort of actual physical wavelengths of light that are being emitted by the two squares are the same. It's just that A looks darker to us than B because of the context. So this isn't super relevant to our topic today, but I thought it was kind of fun to have a little optical illusion there to get us thinking before we jump into this week's topic. Great, so now that most of you guys have joined, I'm just gonna do another quick recap of how these webinars will run. So I'm gonna be leading the webinar, and you can ask any questions that you need to during the webinar, and Ms. McGinley and Mr. Lamb will answer your questions, and then they can also pass them back to me if there's any questions that you guys would like me to answer. And this webinar will be posted to your Google Classrooms after the webinar, so you don't need to memorize it because you can refer back to the webinar and to the webinar slides when you're doing your work for this week. So there's going to be also some time for Q&A at the end if there's any questions that you guys would like me to answer. So your work for this week, as usual, will be to complete the Google form quiz that will be in your Google Classrooms. And then again, Miss McGinley has made a video showing you guys a practical about refraction, which is one of the topics for this week. So you guys can use the practical sheet and then her video to do a practical at home. Or then there's also going to be questions posted on Google Slides in your Google Classroom for you guys to work on as well. So you can do either of those two activities. So the success criteria for today. So by the end of the day, you guys, or by the end of the webinar, you guys will know a little more about reflection. So you guys will know that in reflection, the angle of incidence is equal to the angle of reflection. You guys will be able to compare reflection from a smooth surface to reflection from a rough surface. You guys will be able to explain why light is refracted when it crosses the boundary between media. And you guys will be able to interpret some ray diagrams showing what happens in reflection and refraction. So the key points from this webinar are going to be, how do we see things? What is reflection? And what is refraction? So these are all topics that relate to light waves. So our topic is going to be light waves for this webinar. Before we get started on this week's topic, I just wanted to take another moment to say, great work again last week. So a lot of you guys tried the practical that Miss McGinley explained to you guys. And the point of this practical was that when you were using your microwave and the bar of chocolate to find the speed of microwaves in your microwave oven, if you had the most precise equipment in the world, you would have been able to find that the speed of light was equal. So the speed of the microwaves in your microwave oven is actually equal to the speed of light. And some of you guys got an answer that's actually really close to the speed of light, so that's excellent. But even if you didn't, that's great because you guys tried the practical and you guys showed scientific thinking and problem solving. So just again, really, really great work last week. Great work on the practical and also on answering the questions in your Google Classroom. That's excellent. So thank you guys for that. So on to this week's topic. So let's start with another brief recap of what visible light is. So again, we remember from last week that visible light is a form of electromagnetic radiation, and it is a transverse wave that travels in straight lines. So again, remembering that a transverse wave is a wave where the direction of energy transfer is perpendicular or at a right angle to the direction of oscillations in the wave. So in a transverse wave, like light, the oscillations are going up and down, and the energy is being transferred forward. And now again, visible light is only a really small part of the electromagnetic spectrum. So this is electromagnetic radiation with wavelengths between around 740 to 380 nanometers in wavelength. And the wavelength of the radiation determines the color of the light. So the form of visible light with the longest wavelength is red light, and the form of visible light with the shortest wavelength is violet. And all the other colors fall in between these. So the wavelength of the color, or the wavelength of the light, determines the color that we see. Great. So how do we see things? So our eyes detect the light that's reflected from objects around us. So remember last week when we were talking about how the color of an object that we see is the wavelength of color that's reflected, and this is what we see. So light from the sun is white light, and this contains all the different wavelengths of light. And some of these wavelengths are absorbed by an object and others are reflected, and the colors of the light that are reflected are the colors that we see. So if I've got like a green marker here, this is absorbing all the colors from the sun that's coming from my window, and then it's only reflecting the green wavelengths, and that's why I see it as being green. And the same thing with this tree that I've got in this diagram here. The tree is absorbing all the colors from the sun except for green, and it's reflecting the green light, which is then detected by our eyes and on our retinas, which then pass the information along to our brain, which is how, and then tells our brain that we're looking at a green object, so the green tree. So the key point to remember here is that the colors that we see, everything that we see is reflected light. So if we're in a room, if we're in a dark room that has a bunch of different colorful objects, we're not going to be able to see, oh, Hang on, it stopped. Oh, sorry, it stopped sharing my screen for a little bit. I hope it's all good now.
Yep, all good.
All good. Okay, cool. So yeah, so if we're in a room that's dark, but there's a lot of colorful objects around us, we don't see anything. And that's because there's no light there to be reflected. So if we've got this green marker in a dark room, it's not going to look green to us. We're not going to be able to see anything because it's not reflecting any light. So in order for us to see something, there has to be a source of light for then us to be able to detect the reflected light. Great. So I've got another picture here that's showing how this happens. So in this diagram, I've got a cup of tea. I've got a cup of tea and I've got a light bulb and I've got an eye. So the reason we're able to see this cup of tea is because it's reflecting violet light from the light bulb, and then it's reflecting this to our eyes. So we're able to detect this light and see the cup. If there's no source of light, we're not going to be able to see anything because there's not going to be any light there for it to reflect back to us. Great. So now I have a poll question for you guys. So I have a diagram here showing a person who's working on his laptop and he's seeing a reflection on his laptop screen of the lamp. And I've drawn some light rays here, and I want you guys to tell me if you think there's something wrong with the way I've drawn the light rays. So if I could have the poll up, Ms. McGinley. Oh, hang on, there, yeah, sorry. I showed the answer for a split second there. Great, a bunch of you guys are voting. I'm just gonna give 20 more seconds for the rest of you guys to get your votes in. Thank you guys for participating so well. Great, so many of you guys are saying that there is something wrong with the way I've drawn the light rays, which is correct. So these are not drawn correctly. The way they should be drawn is like this. So in the previous diagram, I had the rays of light going from the laptop screen to the lamp and then to our eyes, but that can't be right because the laptop screen is reflecting the light from the lamp to our eyes. So the ray of light is going from the lamp to the laptop and then being reflected to our eyes. And you guys caught my mistake there, so that's excellent. So for the next section of the webinar, we're going to go into more detail on reflection. So how does reflection occur? So how does the pond reflect this beautiful mountain back to us? Why are we able to see it in the pond? So this is because, pardon the siren outside. So when a ray of light hits a smooth surface like a mirror or a smooth pond of water or the our phone screen or something like that, it's reflected. So when we see these diagrams that are showing reflection, we often see it like this, where we've got an incident ray of light, which is the ray of light that's coming in towards the mirror. Then we've got the reflected ray that's being reflected from the mirror. And then there's this dotted line in the middle that's at a right angle to the mirror. And this is what we call a normal. So this is just this imaginary line that we draw there to help us diagram these rays of light and make sure that they're coming at the right angles. So again, here, the incident ray of light, the way you can remember that the incident ray is the ray of light that's coming towards the mirror is because it's incident, it's coming in, and then the reflected ray is the ray that's reflected. So now I've got another poll question for you guys where I'd like you to identify these three key terms. So the incident ray of light, the reflected ray of light, and the normal line in this diagram. So which letter is referring to which of these key terms? If I could have this pull up, Ms. McGinley. All right, again, I'm going to give you guys some time to get your answers in before I go over the answers. I'll give you guys 15 more seconds to get your answers in before I start going over the answers. A few of you guys are still voting, so 5 more seconds. Great, so you guys did great on these questions. So for question 1, which letter represents the incident ray? So that's C, that's the arrow that's represented by the letter C, because this is the ray of light that's going in towards the mirror from the torch. So that's the incident ray. Then the reflected ray is the ray that's being reflected from the mirror towards our eye. So that's B. And then remember again, the normal is the dotted line that's perpendicular or at a right angle to the mirror that we use to help us in these ray diagrams. So really great job on those questions. Let's go a little more in detail on reflection now. So there's this law called the law of reflection that states that the angle of incidence is equal to the angle of reflection. So in this diagram, you can see that the angle of incidence is the angle between the incident ray of light and the normal, and the angle of reflection is the angle between the normal and the reflected ray. And these two angles are always going to be equal in reflection. So the angle of incidence is always going to be equal to the angle of reflection. So the angle at which the incident ray is coming towards the mirror is going to be the same as the angle that the ray is going to be reflected away from the mirror. So now I've got some more poll questions where you guys can use your knowledge of the law of reflection to answer these questions. So in this diagram, I've got a lamp and there is an incident ray coming from the lamp. So which of these rays here, so S, R, Q, or P, is showing the angle at which the reflected ray is going to travel. And then there's also another one asking some more questions about the angle of incidence and angle of reflection. If I could have the next polls up, Ms. McKinley. Great. Thank you very much. And again, I'm going to give you guys plenty of time to vote for your answers before I start going over them. All right, great. Thank you guys for voting. I'm just going to give you 10 more seconds for anyone who hasn't gotten their answer in yet. Great. Really good job on these questions. So for question 1, which line shows the direction of the reflected ray of light in the diagram? Well, this is going to be Q, and that's because the angle of reflection is equal to the angle of incidence. So the angle between the ray of light coming from the lamp and the normal line, which is this imaginary line perpendicular to the mirror or at a right angle to the mirror, this angle is going to be the same as the angle of the reflected ray. So that means that Q is going to be the ray of light that's reflected. And the same principle applies for question 2. So if a ray of light hits a mirror at an angle of 30 degrees from the normal, what is the angle of reflection? So the angle of reflection is going to be 30 degrees because the angle of incidence is the angle between the incident ray and the normal, so that's 30 degrees, and the angle of reflection equals the angle of incidence, so it's also going to be 30 degrees. Great. So for our final, now we're just really briefly going to talk about how we see images in mirrors. So if there's, if we're looking at this cake in a mirror, we can see it even though we're not looking at it. And that's because these reflected rays of light from the cake are being reflected from the mirror and then arriving and then detected by our eyes. So that's how we can see objects in a mirror. And then in this diagram, just to remind you guys, I've added a sun because we need to remember that the cake itself is not like spontaneously, randomly producing this light. The rays of light that we're seeing from the object are also always going to be reflected from a light source. But when we look in a mirror, we can see the image of the cake because of the way that the light is being reflected by the mirror and then to our eyes. So reflection is how we see images in a mirror. So that's how a mirror works. But then why do we only see reflections in smooth, flat surfaces? So why do we only see reflections in, mirrors and windows and like very smooth water or ice? Why don't we see reflections in everything that we're looking at? That's because there's actually two different kinds of reflection. So there's this thing called specular reflection, which is the kind of reflection that we're familiar with. So this is what happens with a mirror or in a really flat, smooth surface, is the incident rays are all going to be directed or all going to be reflected in the same direction. So we see this nice reflection, this perfect reflection of an object that we're looking at in a mirror because of the way the incident rays are reflected by the smooth surface. However, if we're looking at a rough surface, the surface is going to be really rough and have little bits going in all different directions. So when the incident rays are hitting the surface, they're going to be reflected in a different direction depending on the angle of the surface. So that means that all of the reflected rays are going to be going in a bunch of different directions. So the reflected light is going to be scattered. So this is why it's called diffuse scattering or diffuse reflection. And this is why we can't see a reflection in rough surfaces. So I have just some pictures to help you guys understand what's going on here. So I've got, you can use any object, but I just used a little jar of Marmite. So if I put a jar of Marmite on a smooth piece of aluminum foil, even though the reflection is kind of distorted, you can more or less see a reflection in the aluminum foil. And now this is because the reflected rays are all going in the same direction because it's a lot closer to specular reflection than it is to diffuse scattering. But then if we crumple up the aluminum foil, we're not going to be able to see that reflection anymore. And this is because the crumpled aluminum foil has a bunch of different bits going in different directions. So the light is going to be reflected in a bunch of different directions, and we're no longer going to be able to see that reflection. So this is just an example that can help you guys think about specular reflection versus diffuse scattering. So when the light is scattered, we can't see a reflection anymore. So if I could get this next poll up to ask you guys a bit more about this topic. Yeah, yes, great, thank you. So I'll just give you guys a few more seconds to get your answers in. Great, so I'm going to give you guys 10 more seconds to vote for your answers before I go over the answer. Great. So you guys are doing really well on this question. So why don't we see a reflection in a rough surface like the wall or a piece of paper? So this is actually not because all of the light is absorbed by the surface. Depending on the color of the object, some light is going to be absorbed, but some wavelengths of light are going to be reflected. But then whether or not these are reflected with specular reflection or diffuse scattering determines whether or not we're able to see a reflection. So if the light is reflected in a bunch of different directions, like it would be from the wall or a piece of paper, we're not going to be able to see a reflection. So diffuse scattering is the reason why we can't see reflections in rough surfaces. And specular reflection is the kind of reflection that happens when you're looking at a smooth, flat surface and you can see that reflection. So really well done on this question. So the next topic that we're going to look at is refraction. So refraction is what's happening in these pictures. So you guys have all probably seen something like this. Like for example, when you put a straw in a glass of water or something, and it looks like it's bending or breaking. This is because of this thing called refraction. So refraction happens when light passes from one medium, and now remember, medium is the word that we use to talk about whatever the wave is traveling through. So this could be air, this could be water. So in all of these pictures, we've got two different media. We've got air and water. So when light passes from one medium to another with a different density, it changes speed, which causes it to change direction. And this is called refraction. And remember, density is just how closely the particles are packed together in a substance. So different substances will have different optical density, and then this determines how fast the light is able to travel through the medium. So in this picture, I have a diagram showing what happens when a ray of light travels from air to water. So when it arrives at the boundary between air and water, it actually changes direction because it's going slower in the water than in the air. So it sort of bends a little, so it changes direction. So again, in this diagram, we've got that normal line that's going perpendicular or at a right angle to the boundary between the air and the water. So you have your incident ray, and then it changes direction as it passes into the water. And I'm going to just stop sharing for just a second so I can show an example of why this happens. So I'm going to use this example of a car. So here's my car that's traveling along a road to illustrate how refraction happens and why it happens. So refraction happens because a ray of light changes speed, which causes it to change direction. But why does this happen? So let's look at this car that's traveling along a road, and it's going quickly along the road because it's a nice smooth road. But then if it goes off of the road, it's going to go slower because there's grass, there's more friction, maybe it's muddy. So the car is going to go slower in the grass than it does on the road. So if it's traveling along an angle along the road, and then one of the wheels crosses into the grass, this wheel is now going to go slower than the wheel that's on the road, which causes the car to turn. So it turns as it goes into the grass. So because the car slows down, it turns. So this is effectively what's happening. I'm going to start sharing my screen again. So this is effectively what's happening when light is crossing from air to water. It's slowing down, which causes it to change direction. Great. So again, when light passes from a less dense medium like air to water, the angle of incidence, so again, the angle that's between the normal line and the incident ray, is greater than the angle of refraction. So it's bending towards the normal. But when light passes from a more dense medium to a less dense medium, the angle of incidence is smaller than the angle of refraction. So I'm actually going to just stop sharing my screen again so I can use some diagrams to show that. So yeah, so here I've got a diagram again that's showing how a ray of light is traveling through the air, and then it's meeting the boundary between air and water. So here's my boundary, and then I've got my normal line again here. So you can see that the angle of incidence when light is crossing from air to water, the angle of incidence, so the angle between the incident ray and the normal line, is greater than the angle of refraction, or the angle that's between the normal line and the refracted ray, when the light is crossing from a less dense medium like air to a more dense medium like water. But what about if the ray of light were crossing from water to air? So here again, I've got this boundary between the air and the water, and I've got my normal line, so the dotted line that's perpendicular or at a right angle to the boundary. And I have my incident ray here, so the ray of light that's going in towards the surface. And remember, this light is passing first through the water and then crossing into the air. So our angle of incidence in this case is going to be smaller than the angle of refraction, because it's crossing from a more dense medium where it's traveling slowly to a less dense medium where it's traveling more quickly. So the angle of incidence is going to be smaller than the angle of refraction. Great. Okay, I'm going to start sharing my screen again. And one more thing to remember about refraction is that the light bends back to the original direction when it returns to the original medium. So in this diagram, we've got a ray of light that's passing through the air. So it's going quickly through the air, and then it's crossing the boundary between air and glass. And as it crosses this boundary, it slows down and it bends, right? So now it's traveling more slowly through the glass, but then again, it crosses a boundary between so it crosses the boundary between the glass and the air. And as it crosses into the air, it speeds up again. So it changes direction. And now it's going in the same direction as it was previously in the air. So when the light goes from the air to the glass and back to the air, it's going to start traveling in the original direction when it crosses back into the air. So for example, if we were thinking back to the example of the car and the road, as the car travels along the road, it's going at one angle, then it slows down as it goes off the road, and then it speeds up again as it goes back on the road. So it changes direction when it crosses into the grass, but then it changes direction back as it crosses back onto the road. Great. So this is what explains why this happens. So why things look funny when half of it is above the water and half of it is below the water. And that's because the air changes direction when it crosses, or not the air, the light ray changes direction as it crosses the boundary between two media. So when we're looking at this polar bear, the light is coming straight at us from the air, but then it's sort of changing direction when it goes from the air and from the water to the air. So it looks like it's, head and body are in a different place. And the same thing happens when we're looking at the duck and when we're looking at the straw in the water. So Miss McGinley has made a video that teaches you guys how you can observe refraction using a glass of water and a coin. And then there's also a practical sheet that goes along with that where you can answer some questions about refraction. So these practicals are just to get you thinking about why refraction happens and to help you guys observe refraction as it's happening all around you. So, and the final point about refraction is that refraction also explains why we see rainbows in the sky and when we shine a light through a prism. So this happens because the white light that contains all the different wavelengths is dispersed as it travels through the prism because the different wavelengths of light are refracted by a different amount. So this causes the different wavelengths of light to be separated and we see a rainbow. So I have a video that explains that in more detail to you guys, if you guys would like to watch that video and learn a bit more about why rainbows happen, because this all has to do with refraction. So refraction is interesting because it explains a bunch of different phenomena that we see all around us. Now I have a final set of poll questions for you guys to answer. If I could have those up, Miss McGinley. So these are just a few questions asking about refraction. So yeah, great. I'll let you guys read those questions and get your answers in before I go over the answers. So I'll just give you guys 30 seconds or a minute to answer these questions before we go over the answers together. So great, thank you all for voting. I'm just gonna give you guys 10, 15 more seconds to get your answers in before we go over the answers together. Just a few more seconds. All right, great. So let's go over the answers. So you guys did really well on these questions. So for question 1, why does a pencil in a glass of water look like it bends? And so this is because of the refraction of light. So remember, light changes direction when it crosses from the air to the water because it changes speed. And this causes it to change direction. So this is why when we look at a pencil that's going from the air to the water, it looks like it's bent. So this is due to refraction. And then question 2 was a true or false question. So the angle of incidence is smaller than the angle of refraction when light passes the boundary from air to water. So this is actually false. And I've got a diagram on this next slide that's showing you why. So remember, here's our diagram that's showing what happens when light crosses from air to water. And as you can see in this diagram, the incident ray is going towards the boundary between the air and the water at the angle of incidence, and then the angle of refraction is the angle between the normal and the refracted ray. And the light slows down as it goes from the air to the water, and it changes direction. So this angle of refraction here is actually smaller than the angle of incidence, And that's because the light is going slower in the water than it was in the air. All right, and then the final question that there was is a true or false question. So refraction occurs because light changes frequency when it crosses from one medium to another. And this one is also false. And that's because refraction occurs because light changes speed when it crosses from one medium to another. So again, you can think of that example that I was showing with the car. Whereas the car went from the road to the grass, it slowed down, and this caused it to change direction. So the light ray is changing direction because it's slowing down or speeding up as it crosses from one medium to another. Great. So your work for this week is going to be to complete the Google form quiz. So that'll be posted to your Google Classroom. And then you can either watch the practical video that Ms. McGinley has made and use the practical sheet that she made that goes along with that to try a practical at home. So this is going to be a practical where you can try a couple different examples of refraction and you can observe refraction, or you can work on some questions that have been posted in Google Slides on your Google Classroom. And that's all I have for this week. So there's a few extra videos that you can watch that explain some of these topics. So there's the practical video that Ms. McGinley made, and then there is a video that I made showing how a rainbow forms, and then a summary video that's just going over the basics of reflection and refraction in case you want a sort of short recap of the topics that I covered in this webinar. So now is some time for some Q&A. If you guys have any questions that you'd like me to answer. I'll just wait a little bit if.
Not any at the moment, Miss. Just a few about the work and things. But as always, it will be in your Google Classroom. And if it's not in there yet, then it will be put in there. Now, sometimes we hold off on putting the work in the classroom during the webinar just so that you try it after you've watched the webinar.
All right. Are there any other questions there, Ms. McGinley?
No.
Cool. All right. Well, thank you guys all for participating. That's great. And yeah, have a great week. Thank you very much.
We have lots of thank yous from them.
All right. Well, thank you guys for participating. You guys did really well on the poll questions. It was great to see you guys sending all your answers in. That's excellent. So thank you very much. And yeah, have a great week and be sure to ask your teachers if you have any questions on the work. All right. Thank you.